Good morning, good afternoon, good evening, everybody. This is Nadia Pinardi talking, and I will introduce the webinar of today. The webinar is organized by CMCC, the Euro-Mediterranean Center for Climate Change. So CMCC is a leading research centers focusing on the understanding interaction between climate change and society. And the mission is briefly schematized on three topics: advancing climate research through multidisciplinary analysis, combining climate modeling, environmental economics, and supporting science-driven adaptation and mitigation actions. The research infrastructure, CMCC has a very large research infrastructure. Three multidisciplinary research institutes throughout Italy, and four strategic programs, but most importantly, a computing infrastructure dedicated exclusively to the study of climate change. And in addition to that, two specialized centers on digital innovation, education, and training. CMCC holds many lectures, and some of the latest ones are here. And we like to be inspired by leading experts in climate science and policy. And so you can see from the QR code here the previous CMCC lectures, which are always useful to revisit. The questions and answers will be done after the seminar today. If you need to intervene or ask questions, write it in the Q&A section. Today, I'm very happy to introduce our lecturer, Professor Samantha Siedlecki from University of Connecticut. Samantha is a world-leading expert in biogeochemical forecasting at multi-year timescales, including marine habitats shifts. She has achieved her degree, a PhD degree at the University of Chicago on a very important topic, which is the role of bottom boundary layer in biogeochemical cycles. So she's overall, you would say, an expert on very important carbon cycling and also the coastal part of it. She is at the moment associate professor at the Department of Marine Science, College of Liberal Arts and Sciences at the University of Connecticut. She is holding now a CMCC Bassi fellowship that allows her to come and work with colleagues at CMCC. And she's also part of the scientific steering committee and a big interpreter of our UN Decade program, Coast Predict, UN Ocean Decade program, Coast Predict. And now it's time to leave the floor to Samantha. And thank you for being with us.
Thank you, Nadia, for that nice introduction. I'm excited to be here. Okay, so today I'm going to talk to you about some coastal projections we have been working on for the Northern California current system. If you don't know what that is yet, I hope you will after my introduction. This work was done as part of a larger group project, and some of the main results that I'll show you are my postdoc, Yifan Zuz, whose name is bolded there, but the rest of the team is also listed, and I'll give you a little bit of overview of the project as well. This background view is a view from the Quinault Indian Nation Reservation, and they, are on the outer coast of Washington. And so that you can just get an idea of what the coast looks like, where I'm going to be providing some projections. So a little background on ocean acidification. So ocean acidification occurs in the ocean when CO2 is absorbed by the ocean and pH is reduced in a predictable way. You can see that here from this long time series that's been observed in Hawaii from in the atmosphere from the 50s. That's here in the red line here from Station Mauna Loa. And then nearby at Station Aloha, we have some in-water observations that have been going on since the early 90s, late 80s or so. And so you can see as CO2 rises in the atmosphere, the CO2 in the PCO2 in the surface waters matches that atmospheric trend. And at the same time, the pH shown here in blue on this axis over here declines. And so we have these long-term observations. This is one of the longest on the planet. And I also want to emphasize how important having these long-term observations are, as some support for this particular time series has been called into question recently. But it's invaluable to kind of showing that we understand what's going on in the system on various timescales. So in addition to pH and PCO2 for ocean acidification, we also monitor something called saturation state, which will be shown as this omega symbol in general throughout the presentation. And what omega shows us is how close the system is to an energetic condition for calcifying organisms. So for organisms that make shells out of calcium carbonate, like is depicted here for this pteropod, but there are also oysters and clams and other organisms as well that use this mineral to fortify their shells or carapace's morphology. So the saturation state, when it's above 1, it's energetically favorable to precipitate this mineral for the organism, and then as it gets below 1, it's more energetically favorable for that mineral to dissolve, so it's more difficult. It requires more energy by the organism to maintain that structure. So these are the 3 kind of variables that we monitor, observe, and simulate to understand what's going on with ocean acidification in the ocean. And Earth system models also, simulate these globally. The IPCC only reports surface pH in their summary for policymakers. This is an example from their 2019. But we have, so they do project these surface ocean pH, and they do this with really high confidence. The main uncertainty really comes from the scenario. So not only can we simulate global changes in pH, but we have it's one of the most confidence, like lowest uncertainty variables that the IPCC produces. But globally, it's not clear that while these trends are happening, the magnitudes of them, may be different and modified as you get closer to the coast. So while those big changes are globally are well simulated and predicted, as you move in towards the coast, it's not clear exactly, how well represented those are by those global models. And so there's been a bunch of studies that are some of them are highlighted here. There are more that kind of highlight this change that happens as you come in near the coast for carbon cycling in particular. So one question we have is kind of to what extent can we use global projections to diagnose coastal change for these biogeochemical conditions? And that includes deoxygenation. So deoxygenation, of course, is the loss of oxygen in the water column. And this is from a review by Lisa Levin, kind of showing regionally the different the variability in the magnitude of deoxygenation and sort of the contributions, the drivers of that deoxygenation being different globally and in different regions. And so as you move into the coast, of course, that would also continue to extend. So how do we take these global climate signals and make them more local? We use a method called dynamical downscaling in order to provide localized climate projections for coastal communities. And so the cartoon of that is kind of shown here from a recent paper led by Jason Holt as part of the Coast Predict activity, the FLAME activity, which is the Future Coastal Ocean Climates. And so you can see here the, I don't know if my cursor will work over there, but you can see the large scale global model then with like an inset box, where there's a regional simulation and a sub-regional and a local. And while those seem like zoom-ins, they are also models embedded within a larger climate model. So you would get from the large scale climate model information, ported to a higher resolution grid that is simulating just that pop-out window, right? And these downscaled simulations are, motivated by a lot of societal drivers, including ecosystem health, coastal hazards, marine economy. But there's also a lot of challenges which are reviewed in this paper. You can check it out for more information. Some of those also were reviewed in an earlier paper by Liz Drinkard, where she talked about what the value is, and you can see that here on the right by comparison of the global climate models, the GCMs on the left side, versus the downscaled simulation for the same region for different variables, how spatially you would see some features resolved differently if you used the global climate model for that region versus the downscaled simulation. And so, for example, net primary production looks different both in magnitude and as well as spatial extent, and then similarly for temperature changes as well as the change in current speed. So depending on the question and the use of the simulation, you might be motivated to have more, resolved spatial information. But the extent to which that the choices that people make kind of, which are broad and reviewed, and here's one in this paper by Liz for the work that had been done up until this point, different methodological choices, there's no real consensus yet about what to do. So whether or not the downscaling method is one way, the resolution is widely varies, whether or not you bias corrected from the global climate model, how many ensemble members you're considering, because these are very computationally intensive, whether or not they've included biogeochemistry, and how long of a time slice did they explore in this climate trends. And so there's been a lot of variability in kind of the methods that people have used up until this point. There's also a product out called Icon Coast, which is this figure is from a paper led by Maurice Mathis in 2024, and I'm showing a different approach, which is to kind of use a different resolution as in a global simulation, using a higher resolution as you get near the coast. So coarser in the basins, and then higher resolution as you get into the coast. And they also found for biogeochemistry that the coast, and historically from the simulation which spanned 1990 through 2014, that the coasts were increasingly taking up more carbon. So these negative values indicate more CO2 uptake. These are CO2 fluxes that are plotted here. And they attribute this in this simulation to local biological response and nutrient delivery from the rivers, right, over this time period. So this is a different methodological approach globally, to kind of resolve the coastal processes responsible for these changes. So what could those be? So there's a varying degree. One of them I just mentioned earlier, which in the last slide, which is of course the rivers and sort of that connection to the freshwater hydrological cycle from the land. But the benthos being much closer to the surface, you end up with a lot more sediment, with sediment exchange being really important for these changes as well. Other processes are similar to open ocean, right, where you have air-sea exchange and sort of water column metabolism through the balance of production and respiration. But that production and respiration again is all happening within that shallow depth range. And then in this case, this is an upwelling system that this particular cartoon is showing. And that's what I'm going to focus on here today as an example. So specifically the California Current region. So on the left, you see a cartoon from a figure from Hickey and Bannis in 2008, which kind of highlights the different like sub-regions within the California Current system and the sort of physical processes important within that. And as you move to the north, sort of north of 44 degrees north or so, you see that it changes from like an upwelling system that's dominated by filaments and jets to one that has more what they call more straight coast upwelling. Also in that region, you can see the bathymetry is plotted as well, and the shelves are a bit wider than in the further south within the California Current region. And there is more fresh water as indicated by those yellow plumes that are drawn in this cartoon as well. In addition, there's more canyons as highlighted by those red cross isobath cartoon lines. And then across the whole California Current system, sort of known retentive regions are highlighted with green. So there's a large eddy feature that exits the Salish Sea there, that large urban estuary where Seattle is found in the northern and connects to the Northern California Current region. On the right, you see a cartoon from Dick Feely's paper in 2018, kind of highlighting some processes within that region of the Northern California Current. So you can see in the cartoon the Seattle and the Salish Sea and the Strait of Juan de Fuca there. From perspective, the Columbia River, so Oregon and Washington. And then subsurface, kind of all of these the biogeochemical interactions and that coupling with the ecosystem metabolism, as well as some important fisheries in the benthos there, kind of shown, and then some subsurface currents, in particular the California undercurrent, which is flowing in opposition to the California Current flowing south in the surface. There's a subsurface return flow poleward, as is common in many upwelling systems. And then some chemistry of the water as the CO2 is being absorbed and by those processes that we talked about at the beginning and ocean acidification is continuing to happen. Okay, so observationally, then if we look again at so Seattle's there in the middle, in the sort of yellow region inside the Salish Sea. There's that Strait of Juan de Fuca again. Looking at the Washington coast, you see now from this perspective, the red area outlines this marine sanctuary where there's been observations for more than 10 years of moorings that are set up alongside several of the tribal nations that live there. And so there's lines of moorings kind of corresponding to each one of the waters that they have been fishing in memoriam. And so regionally, this area is already experiencing ocean acidification, hypoxia, and marine heat waves threatening marine life in the region. We know that in part from these long-term moorings as well as other observations in the area. So Simone Allen did the figure in the background on this analysis on those moored assets. And so I've selected some of those to show you. On the right hand, the top right, the Tayawit Head and Cape Elizabeth are showing you, Tayawit Head is from like pretty far north within the sanctuary, close to the Strait of Juan de Fuca. And then the Cape Elizabeth is the furthest south of that red area. And so kind of even within that section of the shelf, there's a gradient and kind of how often the region experiences ocean acidification and hypoxia events. And so we can see that plotted by multiple years, different colors for the upwelling season, which tends to be from April through September seasonally in this region. And so you can see an aragonite saturation state, which gets below 1, which is that energetic threshold that we talked about for calcifying organisms. You see 93% of the upwelling season is undersaturated for both for Taywood Head, and then 98% for Cape Elizabeth. But for hypoxia, about 14% in that furthest north, so it's actually more normoxic most of the time. And then 44% of the upwelling season is hypoxic at that location for this time period currently. So the region's experienced quite a bit of that. So we are now starting to talk about this as compound change. So compound change is referring to kind of multiple environmental stressors acting simultaneously or sequentially, that often leading to amplified ecological and biogeochemical impacts compared to when the stressors act alone, because it's important for the organisms that we're focusing on to think about these changes happening together. One of those critical fisheries that's at risk is from compound change is the Dungeness crab, which is pictured here. They're sensitive to changes in temperature, oxygen, and ocean acidification variables, and are currently one of the most economically valuable fisheries on the West Coast. And so we're trying to sort of generate more localized climate information to help managers understand what's going to happen there. So this is not the first time that I'm going to show you what we did at first. The first downscaling experiment we did was from a paper I led in 2021, where we used CMIP5 model outputs. A Curtis Deutsch's group produced a 12-kilometer downscaled simulation within those CMIP5 models. And then we used our domain, the Cascadia domain, which is also live ocean for those of you who know, and I'll show you more about that in a minute. A higher resolution simulation within the 12 kilometers. So it was kind of a double downscaled simulation. The atmospheric forcing came from the 12-kilometer Worth model for this simulation. And Flores was used on the 12-kilometer downscaled simulation for the historical. And then, the Cascadia domain was downscaled within that. This approach was a time slice in the past, a simulation of a certain number of years in the past versus a time slice in the future, and then a difference to kind of get that kind of what the change would be. It was not a continuous simulation across time. And we're looking to sort of understand if the downscaled simulation would provide different information to then just using the global climate models themselves. And so one way we used to define that was by comparing it to the Earth system models directly. So if the range of the Earth system models, if the range of the ROMS downscaled simulation, the black line, kind of fell within the range from the Earth system models, then we would say there's no modification. And so Evan Howard, who wrote up the 12-kilometer results, found that there really wasn't any modification for net primary production in particular. Then we looked more into the carbon variables, and we found that the projections that we did for both the 12-kilometer and the 1.5-kilometer domains, were both modified for carbon variables. And so here I'm just showing you saturation state, but in the paper we looked at others like PCO2 and pH. And we found that when we compared the 1 degree model to the ensemble for the 12-kilometer range for various depth intervals, that the range for the ensemble was different significantly than what was provided by the global model. And what's interesting is that this also extended to the Northern California current system as well, but the Earth system models projected a different severity of change than while the direction was similar, the severity of the change was different for each one of these different subregions. So that's what we were calling modification. this was true for the carbon variables only, so not for temperature or oxygen, meaning that ecologists who were looking for future ranges could actually, 100 years out, could use the Earth system model deltas directly. So kind of what was driving the modification then that we found in the carbon variables, and we found that it was consistent with this inclusion, this kind of shallower shelf, and the benthic pelagic coupling that goes alongside of that in the downscaled simulation. In nutrient cycling and total alkalinity that was resolved by these downscaled projections was really important. And that sediment interactions likely played an important role at having this modification in there. There was a parallel group working on this a little bit further south in the California current system. And so Mercedes Pozo-Boyol published a paper in 2021 where she did a continuous mini ensemble of projections from 1980 continuously through 2100 using a time varying dynamic delta approach to generate her downscaled forcing. She used ERA5 directly. And for that ROMS-based simulation. But here you can see the range compared from the Earth system models to ROMS downscaled by those Earth system models for 4 different variables: sea surface temperature, oxygen, nitrate, and chlorophyll. And they found that there was no modification for any of these variables, but they didn't explore carbon in particular. So as part of this 4-year project funded by NOAA and co-led by Francis Chan and Dick Feely, we are trying to support the climate-ready Dungeness crab fishery in the Northern California current region. And so our objective was in the group I lead at University of Connecticut, was to try and simulate the trends of multiple stressors in the historical and projected climate change scenarios using this high-resolution simulation. To help identify and suggest potential management actions to help sustain this fishery. So many projections exist, notably within the California current system already. So you might be asking yourself why. So there's just a subset of those kind of here. This region has quite a few localized climate projections. So kind of why do we need a new one? So one reason is that these continuous projections, that method that Mercedes Pozo-Boyol developed, is very attractive also to the additional ecological models on top of that, because you can look at sort of time scale of change of habitat in particular, or the onset of arrival, particularly some stressful variables. And so having a continuous projection in the Northern California current region would be really nice. A lot of them have been done using those time slice differences before. We also found a downscaled an atmosphere, high resolution atmosphere product to use. ERA5 is a 30-kilometer resolution, so we wanted to use something a little bit higher res. Found one that was 12 kilometers. No projection exists like that's continuous and includes a higher resolution atmosphere with the estuary and river forcing. We have 45 rivers in our simulation for the Salish Sea and the Northern California current shelves. And so it's possible, since we've already shown that modification of the global rates by local processes is important, that the method could be responsible for whether or not we see that modification in this region. Wanted to explore it. So we're using an existing tool in the region called LiveOcean, which currently you can go to a regional IUS portal called NANUS and visualize the 3-day forecast for ocean acidification variables right now compared to the moored assets in the region. And so it's a tool that's been around for almost 10 years and that's widely used by the community. It's very realistic. Has tides and rivers, and this version uses a regional wharf model and a HICOM for ocean conditions. But to run it for this long time period, we had to make some changes. So in order to run LiveOcean for 30 years, we had to change the boundary conditions to GORIs from HICOM, and we also had to use a different wharf downscale simulation. That's 12 kilometers, a little bit coarser than what the short-term forecast uses. We also needed to use a 2-kilometer grid instead of the 1.5 in order to run it for this long time period because it's very computationally intensive. It takes about 6 months to run the 100 years of computation time on our system. At the boundaries, we used a biogeochemical machine learning product called ESPER that derives carbon variables, including an anthropogenic carbon content change from basic hydrography. And that's detailed in a paper from Brendan Carter et al. In 2021. And the Blue Carbon Canada group is the ones that, led by Professor Julia Baum, were the ones who provide us with the regional WRF. And I mentioned already the 45 rivers. Okay. So we did a lot of performance testing with this end users in mind. Coming back to this figure where those moored assets are, we certainly compared the output to those. There's a map here on the right showing you all these other assets in the region and observations that we used and compared against that ranged from cruise data, CTDs, bottle data, whatever we could really get our hands on. And there's only a couple of locations that have multi-decadal observational, so those long-term observing data sets, there's not very many of them in this region, despite all of these observations. Those include line P, which is highlighted in bright pink in Canadian waters, and the Newport line, which is off the coast of Oregon, also in pink. And so those two time series let us kind of analyze and evaluate the multi-decadal change. So starting off with some mooring comparisons, I'm just going to show you one. We've done a lot more of these, but they were out there for more than 10 years. And so we have some observations, over a fairly long time period, but not multi-decadal. And so we feel confident that the model is doing a good job at simulating the sort of event scale all the way up to interannual in some of these locations. We also kind of, like I said, looked at those trends for certain locations. And so this is showing you for P4 from line P, the surface trends for PCO2, pH, and saturation state, those 3 variables that were used to monitor ocean acidification. There's a paper out there already by Franco et al. From 2021 that had published these observed trends. And so we're comparing them 3 different ways on this plot. So the blue are the observations, and the rates are the ones that were published in that Franco et al. The model, if you were to use a model is higher resolution in time than the sampling. And so if you were to just use, the kind of daily output to compute change, you would get the gray values. But if you extract the model from the same sampling as the observations, then you have the black values, which are much more in agreement. But these kinds of comparisons also can help us to help inform future monitoring plans for wanting to capture this multi-decadal change in terms of the frequency of sampling in particular, which these values do seem to be sensitive to. And there's Yifan, the postdoc who is responsible for this work in the right corner. Yifan also plotted these simulated trends as maps from the simulation. So on the left, you have the temperature change. On the top is the surface, and the bottom is the bottom. In the middle is the deoxygenation, so the rate of DO change, surface and bottom. And then the saturation state is just one value from the suite of carbon variables, just to give you a sampling of kind of what the multi-stressor compound change looks like in this region. And then I have like some ranges there of what people have published from the region for oxygen, some values from the warming rates that were published over 20 years ago now. Just to give you an idea of how that compares. But notably, you'll see that the surface is warming faster than the bottom is. And so as a benthic organism, you're experiencing different change than if you lived at the surface. The deoxygenation, though, you would be experiencing more severe change at the bottom, as well as for saturation state. The changes in the bottom layers are more severe. We also compared these trends on the shelf relative to the changes in the source waters for this upwelling system, so kind of more off shelf. And so what you're looking at here are the mean rates of change for oxygen at a certain density interval. This is 26.3. So that the slope is in purple over latitude on the y-axis, and then the rate of change is what's plotted on the x-axis for 3 different variables. So the first one is oxygen, second one is total carbon, DIC, so dissolved inorganic carbon, and then the third is nitrate. And what you can see is that the orange line, which is on the shelf, regions less than 200 meters, the rate of change is more severe for each one of these variables. So basically showing that there is a trend in the source waters that's consistent with anthropogenic trends for DIC and deoxygenation for DO, that on the shelf, those source waters are that trend that's well characterized and observed in the basin is amplified even further by coastal processes. So what could be contributing to that long-term historical change? The upwelling intensity obviously is one to think about in this upwelling system. There's source water compositional changes to consider, and mixed layer depth changes have been explored in other work that we did as well. So to estimate the upwelling change, we used an in-water based metric called QD and Beauty, which was developed by Mike Jaycox in paper in 2018. And this gets at the band of wind-driven upwelling at the base of the mixed layer associated with the elevated nitrate concentrations that are experienced during upwelling. So QD is mostly the volume flux, and then Beauty includes nitrate at the mixed layer in order to understand the nutrient, the vertical nutrient. And this was calculated at all those different bins within the domain that you see on the left. And I'm just going to show you results from a couple of those for simplicity. So one from the Washington shelf and one from the Oregon shelf. So on the top, you see the time series of Beauty there over the entire historical simulation. And the bottom, you see 2 time series, the northern one from Washington and the southern one from Oregon over the time series for mixed layer depth. What we found were that there was not very significant changes in either upwelling index, the QD or the Beauty, but there were changes in the significant changes observed in mixed layer depth over this time period, and that's indicated by the star next to the rate and the red lines on those trend plots. And interestingly, the nutrients at the nitrate changes at the mixed layer depth were also insignificant. I'm sorry that got cut off, but the nitrate changes at the mixed layer depth are also insignificant. So, the mixed layer depth is shoaling over this multi-decadal simulation. And so the implications of this are that the nutricline is shoaling alongside the mixed layer depth. And I didn't show you this, but there isn't really that much big of a change of nitrate, not significant in the source waters. So the nutrients in the source waters for the upwelling are not changing. The nutricline is shoaling, and the mixed layer depth is shoaling on the shelf. And so this is consistent with the idea that nutrients are increasingly retained on the shelf over time. And that there's a decrease in ventilation over time as well. So this is depicted here by this cartoon showing that mixed layer depth historically was deeper and then has shoaled over time. There has also been an increase in biomass and over that time period. And so there's more particles on the shelf. Because it's a seasonal upwelling system, there's also a seasonality to consider here. And so at the onset of the upwelling season, you might not have many particles on the shelf. Over the course of the upwelling season, you get more respiration there in the middle as those particles and that benthic pelagic coupling kind of occurs over the course of the season. And then in the fall and over the winter, you get this downwelling, which kind of mixes the shelf, ventilates the shelf, and kind of exports material. And a shoaling mixed layer depth suggests that that ventilated region of the shelf is decreasing over time, right? And that, that more particles are retained. And if we calculate the inventory of particles on the shelf just less than 200 meters over time, we find a significant increase over this multi-decadal, suggesting that there's more retention going on, which is, of course, contributing to the compound change that we observe. So some particular maps of interest for the benthic ecosystem and for coming back to the crabs, where their managers are interested in kind of the areas and the regions and how the aerial extent of this compound change has changed historically and into the future. So we started making maps with them. The first is the area of corrosive water, so kind of below this, below 1, the saturation state of 1. So in that energetically favorable for dissolution range of things, the first decade there, the last decade, and then the difference between the two kind of shows you the expansion of that low saturation state water over the shelf, and then it's largely expanding offshore. Right? Then hypoxia, we also looked at the expansion of that over historically, and will continue to in the future simulation, and found that the aerial extent is different than the saturation state, but that it is also expanding and getting more severe, in particular in Oregon. So that just brings me to the end here, concluding that these shelf processes greatly increase biogeochemical changes in the Northern California current system, and that surface and bottom waters are changing at different rates, and this requires separate monitoring of subsurface waters to really understand and characterize that change. Subsurface waters are changing faster than the surface for biogeochemistry historically, and we don't really expect this phenomenon to be well captured by global coarse resolution simulations. The subsurface monitoring is really critical in order to understand those limitations from those global simulations. And upwelling is changing, but not in its intensity, rather in its retention. And that's caused by this mixed layer depth, which is shoaling, and it's modifying the coastal rates of change for multiple stressors in the region. Crabs have had increasing exposure over the past 30 years to hypoxia and ocean acidification, and that may have caused some habitat compression. There's a group working on a species distribution model for crabs using this model output that I look forward to learning about as we wrap up this project. And so understanding compound change is key to developing these strategies to mitigate marine risks with communities. And these kind of localized projections support those kinds of strategies to protect fisheries and vulnerable marine ecosystems from climate impacts. And our future projections are pending. We're doing SSP, it should be SSP 2, 4.5, and it's in from CMCC, and it's at 2055 and counting. So we're in the middle of that. And I'll just thank the project team and our funding, and I'm happy to take any questions you might have.
Thank you very much, Samantha, for the brilliant and comprehensive presentation. It is very useful to see how also these Earth system models can be used to predict the impact driven by multiple stressors in the marine environment. I'm a senior scientist at the Institute of Climate Resilience. And so I was very interested in listening to your perspective on the compound events in the oceans. And my question is, how could this approach be also expanded more to address the impacts at the land-sea interface and possibly also integrating impacts from drought, but also land use changes, extreme precipitation events, and so on?
Yeah, really good question. We have, river forcing, 45 rivers in this simulation, but they are limited to, we're limited in the way that we simulated the changes within them because we don't have a regional Earth system model, right? And it's not coupled to a regional hydrological model. And so I think that we would benefit from that kind of approach, or something that includes and couples, more further couples the climate system in the region. What we did here was used the historical discharge over the past 30 years that had been well monitored in the region for the majority of the rivers. And we applied, similar to the other forcings, a time varying delta from the Earth system model output for the rivers that were included in that, in that simulation. And so that is, one way of kind of trying to include, right, the kind of coupling it to it wasn't the same as what it was in the historical. We tried to include some of the feedbacks you might expect in the future climate. But that would be, I think, improved greatly by having something that better coupled the land system and the terrestrial system and the role that could play in there. Also, the biogeochemistry that we imparted is constant over this. And so kind of understanding what role the change in the residence time, let's say, of that surface water that might happen from land use changes or whatnot would play in changing the biogeochemistry of those rivers is not something we can explore with this approach that we have here, and would require a kind of a regional Earth system model or another kind of a tool that would incorporate those kinds of changes so that you could explore that. And I think that is an interesting kind of next step or something, to think about in the future.
Yeah, thank you, Samantha. I agree. It would be really interesting to further see developments and cooperate on these in the future. So now I'm encouraging all the attendants and participants to type their questions in the Q&A panel. And there are already 2 questions, so I'm going to read and facilitate a bit the answers for this. So there is one question saying, is wind-driven Ekman transport alone an adequate measure of upwelling intensity, or do we need integrated physical biogeochemical metrics to better capture upwelling dynamics in future ocean?
Sorry, could you repeat the beginning of that one more time?
I think you can also read yourself, because there is the Q&A panel. So it's a long question. Maybe you can also read it. It's related to the relevance of wind-driven transport parameter on upwelling dynamics. Can you read it?
Found it. Wonderful.
Okay, good.
Yeah, so we did not use purely the wind stress, as a proxy for the Ekman transport in this. There's many upwelling indices, right, that are out there. And in this case, we chose one that was in water, that was not wind only, right? That included an ageostrophic component, as well as the wind-driven, because that's been shown in Mike Jaycox's work to change the answer you get for the upwelling intensity. There's also been some recent work done by Ken Brink, as well as some observation work from Ryan McCabe, kind of showing on the Washington Shelf that the kind of depth of the source water changes over time, consistent with this kind of in-water modification. So I think that, so we chose to go with the in-water upwelling intensity measure in order to include feedbacks from stratification, which are also been shown to be important, and would be included in our measure, QD or beauty, rather than just the surface wind-driven Ekman transport, which has been used the longest, I would say, in the literature. But I'm not sure that it's the most, in this case, I'm not sure it would characterize this biogeochemical change as much. But thank you for the question. Hopefully that cleared that one up. Yeah.
Thank you, Samantha. Yeah, we can move to the second question in the chat, which regards the sea-ocean cycle. What do you expect to happen in semi-closed areas and seas, such as the Adriatic Sea, the Baltic Sea, and so on?
Yeah, so in regions where that benthic pelagic coupling would be even more, and maybe the residence time of the water would be even longer than the small shelf, relatively speaking, but that was only about 10 kilometers wide in the Northern California current. So even on that small shelf, we're seeing the impact of benthic pelagic coupling, being important on these multi-decadal timescales. I imagine in a broader shelf region and a semi-enclosed sea that it has even more retention, this would be compounded even further. Yeah, these feedbacks would be even more important to include.
Yeah, thank you, Samantha. There is another very technical question on the MLD shoaling and the intensity of upwelling, how these are related to the thermal versus wind-driven response in this region, and if you did any experiment to separate them out.
Oh, we have not done that experiment. I think that's a really interesting question. We can separate out the wind-driven and this kind of ageostrophic component in that because QD allows you to do that. And that question came up recently and is something that we're working on. But we did not do any experiment to separate out the thermal versus the wind-driven response in the system. I think that would be really interesting to do. Mm-hmm.
Yeah, another quick question is related to nutrient data. They cover a long period. If you have available data on this.
Yeah, also very good question. Nutrient data surprisingly is not as prevalent as the rest of the data sets. And so it has been a real challenge because that would be, I think, important in some of these. So it's not available from Newport. We are looking for it from Line P in order to observationally verify our story as well. And so stay tuned. We're working on that bit, but it's surprisingly nutrient data is not as available as you want it to be. Yeah.
Thanks, Samantha. Another question relates to the rotation of wind stress and how it is aligned with the coastal orientation. And how did you implement this in your?
Yeah, so we didn't have to do that because the model does that, because we provide the forcing from the wharf, and that kind of happens within the one-way coupling that happens between those two simulations. In the output, we didn't analyze the wind field themselves. We chose this in-water measure, and so didn't have to do that kind of a rotation. In some of my past work, we had to do that rotation for the winds. But because, like I pointed out at the beginning, this region is more of a straight coast upwelling, it's more convenient as you move into the Bode area, the Bode coastline of California. Things become more complicated in terms of needing to do that rotation. But Washington and Oregon are pretty straight north-south. As you get into British Columbia, also more of a challenge. But we didn't explore that. We didn't need to explore that directly in this analysis because of the in-water measures of upwelling.
Yeah, okay. Thank you. Another curiosity, I think, is related to the studies in other regions. If you have idea about how the situation is in Bengala, Morocco, other regions worldwide.
Yeah. So I am not sure. I think that, the long-term, I think there's real value to having these long-term historical simulations to extend our observational records, you know, in time and space, especially for carbon, which has the shortest observational record of any of the variables, because of when it was like when observation started for that. And so I think it makes this an increasing priority to kind of expand this approach to different regions, to these different upwelling regions, especially because the systems that you mentioned have a lot of variability in freshwater end members and size of the shelf, to sort of explore how this compound change would be different in those different settings. Yeah, but to my knowledge, these kinds of simulations don't exist for those regions, coupled with the biogeochemistry. But if you know of one, please put it in the chat. Yeah, so I'd like to know.
Thanks, Samantha. I also have a final question, if possible. I'm curious to know if you already used the outputs of your model as a sort of operational decision support tool or useful for the assessment of socioeconomic impacts on fisheries, on protected areas, if you share the output with coastal communities to help them in defining adaptation strategies for the future.
So we are working on with a group of managers of, you know, specifically targeting the managers and end users of the Dungeness crab fishery. And so we have a meeting with them. We just had one in December, kind of showing them these results, and we're working with them to refine those hypoxic area and corrosive volume maps that I showed you, so that they can have products from the future simulation that are relevant to that particular metric as well as others. And then, like I said, there's a group working on the biological side, ingesting this ocean conditions and putting that into the space-specific, species-specific space of Dungeness crab, with a species distribution model that's been designed specifically for that organism, and that will also kind of help to put this ocean change, this compound ocean change, in perspective of the species of interest. Yeah, so work is ongoing there. Yeah.
Okay. I think there are still a couple of very specific questions in the chat. I don't know, because we are also running out of time. First of all, are you going to share maybe the references of your presentation later, if it's possible?
Sure. Yeah.
Yeah. And so I think there is a general interest on this. And
like I could type an answer for some of these more specific technical questions.
Yeah. In the end, I think there is one. Could the remote sensing, in particular ocean color, help you in model validation or understanding of biogeochemistry? Yeah.
We did do some for SST. We did not for the biogeochemistry. It would, because there's a lot of clouds in this region. Anyways, we could yeah go on about that for a minute. But so far we've only used it for SST. I didn't show, but we have.
I think it's okay. I mean, we try to answer all the questions, but hopefully you can be in contact also via email for any specific further curiosity or questions to Professor Siedlecki. So thank you, everyone. Thank you, Samantha, for your time and for the seminar. Thank you to all the participants, and then to the moderators and organizers of the seminar.
Yes, thanks. Thank you very much.